Hi students, welcome to HSC Earth and Environmental Science and Module 7 Climate Science. This is video number 9 and the last in our little kind of mini series on ancient climates. This time we're going to be focusing on changing isotope ratios. So it's the last of these describe and discuss ancient evidence of variations in global temperature, because this time we're going to be looking at changing isotope ratios in rocks and deep sea sediments. So the first thing we need to do is have a little bit of a discussion about isotopes. So this hopefully will just form a small memory jogger. Remember that isotopes basically are something that we talk about in terms of atoms that look at the number of protons and neutrons in the nucleus. So when we look at something like oxygen, and oxygen is number 8, so it will have 8 protons, and the number of protons defines which element we're talking about. So all oxygen atoms have 8 protons, but they don't all have 8 neutrons. Now the most common ones do. So when we talk about oxygen 16, we're talking about 8 protons and 8 neutrons. The majority of the mass of the atom is located in the nucleus. So the electrons are not adding significantly to the mass, which is one of the reasons why we can talk about things like oxygen 16, oxygen 17, and oxygen 18 purely in terms of the difference in the number of neutrons in the nucleus. So that means that if we're talking about oxygen 16, then we're talking about 8 protons and 8 neutrons. But when we're talking about 17 and 18, we're talking about the same number of protons, but for, say, oxygen 18, we're now looking at 10 neutrons in the nucleus of the atom. And this is oxygen 18. Sometimes you'll see it written as 18 and 8 oxygen. And the result of this is that we've got almost a 10%, in fact, probably slightly more than a 10% increase in the mass of this atom. So oxygen 18 are more massive than oxygen 16. And this is one of the keys that we need to keep in mind as we talk about oxygen isotopes. In terms of radioactivity, and we know that there's a number of radioisotopes, and we've talked about how some of those have been used in terms of dating of geological specimens, but none of these ones are radioactive. They are all radioactively stable, if you like. So we don't have radioactivity as part of the story here. What we do have is this. Oxygen 16, which is the most common form of oxygen. In fact, the majority of oxygen is oxygen 16, 99.8% of all oxygen atoms. So that is a very large number. Oxygen 17 is exceedingly rare, and that's pretty much the last time I'm going to refer to it in this video. Oxygen 18 is the key. It's just abundant enough in nature for us to not only measure it, but also to be able to detect changes in its frequency. Now, the key thing here is this increase in mass, because the increase in mass is going to do a couple of things, or at least it's going to have an effect on a couple of things. And the first thing it affects is evaporation rates. So evaporation is the conversion, if you like, of liquid water into gaseous water vapor, and it's kind of removal from that source of the liquid. So if you think about water, that it's evaporating from the oceans, from liquid into a gas, rising into the atmosphere, that's an example of evaporation. Now, because there's an amount of energy that's required in order to turn a liquid into a gas, if you have slightly more mass, then you need slightly more energy. So there's a relationship between mass, which is proportional to energy. More mass means more energy. And therefore, if you want to try and evaporate a large number of slightly heavier atoms or molecules, because we're talking about oxygen now combining with water, with hydrogens to form water molecules. So now to try and evaporate these slightly heavier molecules, you're going to need slightly more energy. And so, therefore, preferentially, we see the lighter isotope, the oxygen 16, are the ones that are more likely to be evaporated. The consequence of that is that we have the slightly heavier isotope, oxygen 18, in slightly higher concentrations back in the liquid part, back in the liquid phase, in the oceans. So this means that if we can see where there are times where maybe there's more heat, more energy, we might get more evaporation, less heat, less energy. We're not only going to get less evaporation, we maybe are more likely to have some of that oxygen locked up in ice. That's one of the things that we're looking at. The third part of the story, I guess, is the fact that we also can look at some deep sea sediments. And one of the things that can be created are carbonates. That is a specific type of negative or anion that is present in the oceans. And again, it involves combinations of carbon dioxide and water, and between them they form the carbonates, or the hydrogen carbonates or bicarbonate ions. And these carbonate ions are very important for the production of a large number of shells, or the protective exoskeletons of marine life. And so again, the deposition of these, if they are then being created out of oxygen-18 and falling to the deep sea floors, maybe we can find some differences in the proportions of these different types of oxygen isotopes as a result of their formation in carbonates as well. Altogether, what we try and do when we put together this picture, we can see that water that is warmed evaporates. It may fall as rain, it may fall as snow, it may form ice, it may form water that runs into streams and rivers, and perhaps ultimately back into the ocean as well. So we've got some cycling that's happening here, and what we're trying to do is to see if differentially there's places where we might find slightly higher concentrations of the oxygen-18 isotope in comparison to the much more common oxygen-16. So that's pretty much what we've been trying to do. Marine organisms take oxygen compounds from the seawater, and so they can be used as a proxy for local water temperature. So where they're taking the oxygen-18 and maybe are using it in the formation of these carbonate ions, or sometimes the bicarbonate ions, the HCO3 minus ions, both of which can be taken into the formation of shell structures, then we have a range of different types of possibilities of where we might be able to track the oxygen-18 isotopes. The sensitivity of the oxygen isotopes means that we can show some very minor temperature variations. So as little as 1 degree of change in the seawater can be sufficient for us to be able to tell the difference based on the relative ratios of the oxygen-16 to oxygen-18 isotopes. Now, the other thing we know about climate change is that climate change can influence ocean surface water temperatures. So this is where we find most plankton. Plankton are found in surface waters, and plankton are those very tiny microscopic organisms that are critical to ocean food chains. Differences in the oxygen isotope ratios of fossils of plankton will also allow us to determine whether or not there's been changes in local water temperatures at certain periods of time. So there's a couple of things that we can do here. We can look at the layer by layer sampling of plankton and see how the isotope, the oxygen isotope ratios have varied over time, to see whether or not that's going to give us any clues about whether there is a slight higher or lower ratio of oxygen-18 isotopes in the past, and what correlation this might have in relation to climate change. So a lot of information here, and some things that we want to just quickly skip through in order to try and make sure that you're across all of these key ideas. So firstly, we can look at the difference between the types of organisms that are found in the lower parts of the ocean. So benthic tends to mean deep part of the ocean floor. Planktonic would be referring to the surface waters. So foraminifera that are found in the surface waters would be planktonic, and those that are found in the deep ocean would be benthic. And so what we've got to do is we've got to try and look at our oxygen-18 isotope values. In order to do this, we've created something scientists have created a value, if you like, known as the delta oxygen-18 value. And so This is a value that basically compares the ratios of isotopes in fossils to the ratio in a standard, so something that we might find happening today. So we know what the climate's like today. We get a bit of an idea of the rough ratio of oxygen 18 to oxygen 16, and that can give us a little bit of a comparison point, which we can then determine whether or not what we're seeing in our fossils is a slightly lower, more negative value, or a higher, more positive value in terms of the incidence of oxygen 18. A change. Delta is just a Greek letter that we use often to signify a change, usually a small change. So we get you might have seen the triangle, which is a large change. That usually just means change. So when we use the lowercase delta, it's generally indicating just a smaller change. So how does this work? Well, higher ocean delta O18 values are indicative of colder climates, and lower ones are indicative of warmer climates. So think about those ideas of evaporation and deposition and how those oxygen 18 isotopes are going to either be taken up into the atmosphere, and preferentially they're not, or absorbed into the skeletal structures of marine organisms, which again they can be. A couple of key points, a nice little summary I think is important at this point to try and bring some of these points together. So I've listed a few of these here. The oxygen 16, the lighter one, evaporates first, and so we find more oxygen 18 in the warmer tropical oceans. When the water vapor condenses, so that is, once we have evaporated the water, it's become water vapor, it then condenses back into a liquid, and it may then fall. If it falls, the water that's rich in the oxygen 18 for the same reason will precipitate first because it's heavier, therefore it will fall faster under gravity, if you like. The acceleration is still the same, but the mass is bigger now, so there's a greater force as a result of that greater mass. Cold polar regions have lower oxygen 18, but we do find more precipitation in some of the lower latitudes. The tropics possess high oxygen 18, but very little of the oxygen 16. So we're starting to see that there are correlations between the proportions. Now remember, we're talking very small changes. So we talked about the fact right at the beginning, we were talking about 99.8% of oxygen 16. This leaves, if there's no or negligible amount of oxygen 17, only 0.2% of oxygen 18. So when we're talking about high and low, little and lots, we're talking about relative amounts here. So still very small amounts of oxygen 18, but slightly higher in some places, slightly lower in others. These two important processes, evaporation and precipitation, are highly correlated with temperature, and so therefore climate change can affect the ratio of oxygen 18 to oxygen 16, and as a result alter their distribution. Likewise, whether we're in a greenhouse age or an icehouse age, depending on how much ice there is near the poles, whether that's retreating or whether that's expanding further away from the poles towards the equators, this can also affect the amount of oxygen 18, and as a result the delta O18 value. The lighter form of oxygen can be locked in the glaciers after it precipitates, so after it falls as rain or snow in the higher latitudes. But in warmer climates, when the glaciers melt, they can release this oxygen 16, and that can enrich the ocean. So we do get some cycling effects that are happening here. The consequence, ice in the high latitudes plays an important role in regulating the delta O18 value. This is where it's important that we can start to look at some of the indicators of where a slightly higher amount of oxygen 18, what that might indicate in terms of climate, and slightly lower values, and what that might also indicate about climate. Some really good resources, both from the Australian Earth Science Education website and also in your textbook, and we will be looking at those one interesting little activity, analysing data, so we'll have a look at that in class. Thanks for watching.